This is Chapter 3, Section 3, Part B. In this one, now that we've been covering some math, we're going to go back and we're going to look at the mole, which is one of the base quantities we've talked about, and we're going to do some molar conversions. And that is a picture of a true mole, not necessarily the chemistry mole. So what is a mole? It is going to be a counting number like a dozen. We are all familiar with a dozen means 12. And the mole is related to Avogadro's number. 1 mole equals 6.022 times 10 to the 23rd items. So if you're talking about a mole of atoms, then you have 6 times 10 to the 23rd atoms of an element or a compound. That is an extremely large number. If we were to write that out, it would look like this. So as you can see, very, very large. And we are using our scientific notation now because, again, who wants to write out that large number every time? So 1 mole, the mole is, again, like a counting number, but instead of it being equal to 12, since that word goes with dozen, it is equal to Avogadro's number, which is 6.022 times 10 to the 23rd. So when we say Avogadro's number, that is the number we are referencing. So if we were to look at something large scale, things that you could actually see and not something tiny like an individual atom, how large is Avogadro's number? Well, if you had 1 mole of hockey pucks, that would equal the mass of the moon. So that's 6 times 10 to the 23rd hockey pucks. If you had 1 mole of basketballs, it would fill a bag the size of the earth. That's a lot of basketballs. And if you had 1 mole of pennies, it would cover the earth a 1/4 mile deep. So again, all of these, if you had 1 mole's worth of any of these, that would be 6.022 times 10 to the 23rd items of each. So, getting into molar mass, you are going to need your periodic table. So if you don't have that and a calculator, baby calculator with you right now, make sure you grab a periodic table and a baby calculator. If we have the mass of 1 mole of an element or compound, that is called the molar mass. So it is going to be the mass in grams of 1 mole of a compound. Well, the mass, if you're talking about an individual element, that mass, the number that goes with it, must come from the periodic table. So now we're introducing you to another phrase, which is atomic mass. Atomic mass is going to tell you on the individual atom scale how many atomic mass units you have per atom. So that is the mass per individual atom. So, atomic mass is going to go with this one right here. It's measured in AMUs, which is atomic mass units. Again, you would use that particular mass unit if you were talking about individual atoms. But if you're talking about a mole's worth of atoms, again, not just 1 or 2 or 3 or 4 atoms, but 6 times 10 to the 23rd atoms, then you would be looking at molar mass, and it is measured in grams per mole. Now, the special thing about these two numbers, if you're talking about individual elements, then the number off of the periodic table, could be used for either one of these. Just your unit would either be AMU if you're talking about atomic mass, or grams per mole if you're talking about a mole's worth of a substance and you need its mass in grams. And we will round each of these to 2 decimal places. So if I'm looking at your periodic table, for instance, I'm looking at hydrogen, which is 1.008. We would write down hydrogen's mass as 1.01. If I'm looking at helium, which is 4.003, we would use 4.00. But you cannot add decimal places. So I am looking at mercury right now, Hg. The mass on the periodic table is 200.6. I cannot add a second decimal place because I do not know what that decimal place is. But we will round the values from the periodic table to 2 decimal places. So if you're going to look at molar mass of a substance, and I've got 3 different examples right here. If I asked you to find the atomic mass of carbon, you would look at your periodic table, and its atomic mass is 12.01 AMU. That means 1 atom of carbon has an atomic mass of 12.1. But if I asked you, well, what's the molar mass of carbon, meaning if you had a whole mole's worth of carbon, that is 6.022 times 10 to the 23rd atoms of carbon. Well, its molar mass is still 12.01, which is the mass off of the periodic table. So again, numerically, same value, but we are either talking about only 1 atom if we're doing AMU, or we're talking about a whole mole's worth of atoms if we're doing molar mass. So for aluminum, I'm looking at the periodic table. If I asked you what is the atomic mass unit for 1 atom of aluminum, you would give me 26.98. If you have a whole mole's worth of aluminum, what is its mass in grams? Well, its mass in grams is going to still be 26.98. So you go and you do zinc. If I want the molar mass of zinc, again, if I have a mole's worth of zinc atoms, it's a lot of atoms, what would its mass be in grams? You should have come up with 65.39, and again, that value is from the periodic table. Now we're going to use these values to come up with molar mass of compounds. So what if you have multiple atoms together, but we have Avogadro's number of molecules of these? So let's start with water. Water's formula is H2O, so it's still in this section I would give you the formula for compounds that are needed, but you would have to know how to do their calculations. So if I asked you for the molar mass of water, again, if I have a mole's worth of water molecules, you would still use the values from the periodic table. So as I look at this, I have 2 hydrogen atoms and 1 oxygen atom that make up a molecule. So finding its molar mass, you have the 2 for hydrogen. There is hydrogen's molar mass from the periodic table. You only have 1 oxygen, so notice we didn't put a 1 out front because 1 times 16, which is its mass from the periodic table, is still 16. When you add those up, you get 18.02. So if you had a mole's worth of water, that is roughly 18.02 grams would be its mass, and I can tell you, knowing I know the density of water, that is roughly 18 milliliters of water. Now let's go do sodium chloride. Sodium chloride's formula is NaCl. Again, I only have 1 atom of each of these that makes up a unit of sodium chloride. So I'm going to get their masses from the periodic table. Sodium is 22.99 and chlorine is 35.45. Again, I've left off the 1s because it won't change our value. So the molar mass of table salt is 58.44 grams per mole. And again, that's assuming you have a mole's worth of those units of salt. Sodium bicarbonate, also known as baking soda. We have 1 atom of sodium, 1 atom of hydrogen, 1 atom of carbon, but 3 atoms of oxygen. So if we were to write this out, sodium, since you only have 1 atom of it from the periodic table, sodium's molar mass is 22.99. Hydrogen from the periodic table, 1.01. Carbon from the periodic table, 12.01. And then oxygen from the periodic table is 16.00, but we do have 3 of those oxygen atoms. So make sure you multiply 3 times 16 first, then you add on the rest of your values. And when you add those up, you get 84.01 grams, or grams per mole, because we are assuming if you're talking molar mass, you must have a mole of the substance. And then sucrose, which is a form of sugar. This one is C12H22O11. So we have a lot of atoms to worry about, but if we have a mole's worth of this sugar sucrose, it would look like this. Again, 12 carbons, 22 hydrogens, and 11 oxygens, and you calculate and get 342. Make sure that you can put these into your calculator properly. So this is how I want you to do your molar mass examples and calculations of those. Now we're going to get into conversions. So with our molar conversions, we're going to be converting between 3 different things. So I want you, definitely what I am drawing right now, make sure you get this in your notes. Moles is our pivot point for everything that we're going to do. And moles is measured in moles. So I already have the abbreviation for the unit moles. Mass is measured in grams. And then our number of particles, I'm putting particles here. Now the particles, since we're talking about chemistry class, we're going to focus on atoms and molecules in this particular unit. It could be units if you're talking ionic compounds. Molecules is for covalent compounds. And then, again, atoms, that's an individual element. We're going to be using Avogadro's number there. So if we're converting between mass, moles, and number of particles, we're going to use the values we've been talking about today. So between mass and moles, that conversion can go either way, and you would be using molar mass to talk about this conversion. We just looked at how to do some molar mass examples, whether individual elements or compounds. And the units for molar mass are grams per mole, and it is understood per 1 mole. And I've told you, make sure you get the grams off of the periodic table. So when you write your notes and you put PT, make sure you remember that's for the periodic table. So the number with grams is going to come from the periodic table. Then we have, you can do conversions between moles and number of particles. And this is going to involve Avogadro's number. Now this setup, I'm just taking the equality statement we saw earlier, the 1 mole equals Avogadro's number of particles. So I'm going to put my particle up here, and again, you're going to see it listed in chemistry in this chapter as atoms or molecules as your particle per mole, and again it is per 1 mole, but the number that you are going to be using for particles is a set 6.022 times 10 to the 23rd, which is Avogadro's number. You do need to memorize Avogadro's number. As far as periodic table goes, on our quizzes and tests, you will have a periodic table to look at. You just have to know how to use it properly. So notice the double-headed arrow. We can go from mass to moles or moles to mass. If we go from moles to mass, just know that this can get flipped over. The 1 still goes with moles in the numerator, and the number from the periodic table still goes with grams in the denominator. So that can get flipped. We can also have this one get flipped if you're going backwards from particles to moles. So again, if you flip that over and moles is in the numerator, the 1 has to go with it. Particles would be in the denominator. Avogadro's number has to go into the denominator. So again, this chart, extremely important. Make sure you get it in your notes. So this was the chart. I just wanted you to see it as it actually unfolds. Now we're going to go work out a few examples. Please get all the examples in your notes. So for the first one, how many moles of carbon are in 26 grams of carbon? Kind of like what we did earlier, the first thing that is always going to go inside of your grid is going to be your given information. So your given information has to go in here first, and the only thing I see given is 26 grams. So I will put 26 grams. Just like when we were doing our prefix conversions with the SI system, you had a number and a unit. Now we have to label the substance. The substance we're dealing with is carbon, so I will put carbon's symbol, which is a C. Also, like previously, whatever unit and now substance we have here must get duplicated there in the denominator because we do not want it in our answer. So I will put grams of carbon right down here so that they match up. The unit that we are going to, how many moles? And if you think about our 3 boxes that we had, I'm just going to do first 2. We can. Sorry about that. But if you think about the boxes, we did have a direct link between grams and moles. So that is a one-step conversion. So I can come down here since grams is in my denominator and put moles right up there in the numerator. And again, I will label my substance. So when I say conversion, this one step right here is considered to be the one step that you're looking at with the boxes. So we are going to go from grams to moles in that one step. And now if you remember the numbers to get for molar mass, because these are the units for molar mass, look back at your 3 boxes. Again, we had it listed up here as grams per mole, the understood one with mole, and with grams, some number from the periodic table goes with grams. So if I come back down to my conversion, a 1 has to go with mole here, and I will go look at the periodic table to find out what number goes with grams of carbon. And on the periodic table, carbon's molar mass is 12.01. Grams of carbon cancels. I'm left with moles of carbon. That is great because I know in my answer I need moles of carbon because it said that's what we solved for. So it's 26 times 1 divided by 12.01 to get your answer. Now we also have to think about significant figures and rounding rules. Since this is all multiply and divide, we are going with the fewest given or total significant figures in a number. Remember, the 1 is considered an exact number because 1 mole is a counting number that we've got. I do have 2 significant figures here. This is a rounded off number from the periodic table already. There are 4 significant figures here, so I will be allowed 2 significant figures in my answer. 2 significant figures in my answer. So when you get your number in your calculator, round it to 2 significant figures. And your answer is 2.2 moles of carbon. Get this next problem in your notes. How many molecules are in 2.5 moles of sucrose? We saw that earlier. Again, how many molecules? Well, I told you again, molecules, you're going to see that is the particle that we are talking about in this example. We put our given in first. So there is my given information. I have 2.50 moles of sucrose. And again, you must label your substance, please, on everything that you do for me. So moles was given. I know that we want to repeat moles right down here. So I've got moles right there. If, again, you think about your boxes, and our boxes that we had, you could have had moles going to particles. Moles going to particles. That was one step. And it was set up as Avogadro's number over 1 mole. Place your unit right over here. This one in this case is going to be molecules. So I will go put molecules. Notice I'm abbreviating it MOLEC because I don't want it to look like moles, that extra C. I know it's going to be molecules of sucrose. So when I put in my values, I have a 1 must go with the moles. And then Avogadro's number right here has to go with our particle molecules. Now we are ready to calculate. In my answer, with again multiplying and dividing, I know that I need either 3 or 4 significant figures. So 3 significant figures is going to be my answer when I round properly. When you get your initial answer here, it will be 15.055 because I am taking the 2.5 times 6.022 dividing by 1. So that gives me 15.055. And then I have to deal with the times 10 to the 23rd. Again, you're using our baby calculators, no scientific calculators, so the rules that we learn for scientific notation have to be used here. Since that is in the numerator and there is not another exponent to add to the 23 or subtract from the 23, it will come over into our answer as 15.055 times 10 to the 23rd. It is molecules of sucrose, but we're going to go ahead and refine this down because looks like we have to move the decimal to get it in proper scientific notation, and we're going to have to round it to the correct number of significant figures, which is 3. So let's start with the moving of the decimal. If I move it over here, 1.5, and we can go ahead and round 2 to 3 significant figures. It looks like the 0 will become a 1 based on our rounding rules. And for scientific notation, I took away 1 spot over here to make it smaller, 1.51. I must add that back to my exponent to get times 10 to the 24th. And then I will add on my molecules of sucrose to get all my proper labels in my answer. So there is my final answer, 1.51 times 10 to the 24th molecules of sucrose. Again, you have to think proper scientific notation and proper number of significant figures after you round. And our last example, looks like they're already giving it away. Looks like it's going to be 2 steps. It says find the mass of 2.1 times 10 to the 24th molecules of baking soda. So there's the baking soda again that we looked at earlier. And I'm going to go back and refresh you on your boxes. On the boxes, I went ahead and I did mass to moles to molecules. And again, all of those can go backwards because in this one it looks like we're going to go from molecules to moles to mass, since molecules is actually given 2.1 times 10 to the 24th molecules of baking soda, NaHCO3. 2.1 times 10 to the 24th molecules of baking soda. Please make sure you're looking at your boxes with all the values underneath them as you go through this. Again, since I have molecules here, I want to repeat that right here at the bottom. So we've got, molecules of baking soda. And we are going from molecules to moles. So I know that my next unit that I'm going to use is going to be moles of baking soda. The numbers, but with that step, a 1 has to go with moles. So you can look back at what you were doing. A 1 goes with moles, and Avogadro's number has to go with molecules. So a 1 with mole, Avogadro's number with molecules. And then, as I notice that this is moles, that has to be repeated there at the bottom. So that is moles of baking soda. And I know that we are going from moles to grams. So I'm going to switch my colors here and get grams of baking soda there at the top. And the numbers involved with that, as I look back, again, a 1 has to go with moles. And the number with grams has to come from the periodic table. Well, this was baking soda. Back earlier, we calculated how to find the molar mass of the compounds. And baking soda was one of those compounds. We found its mass earlier to be 84.01 grams per mole. If you were to come across this problem separately, you would have had to have shown how you calculated the mass of baking soda. You would have had to have shown that calculation separately. So again, anytime you've got compounds like this, show the abbreviated math that we showed earlier to find its molar mass. Now, what are we going to do with all this information? It looks like we are ready to cancel some things out. Looks like moles and moles cancels, molecules and molecules cancels. I am left with grams of baking soda, which is good because grams of baking soda, it said find the mass of baking soda. Let's talk significant figures first. Let's see. In this number, we have 2 significant figures. Again, ones are exact. That number has 4, and this number has 4. So we are limited to 2 significant figures in our answer. Let's look at what we're going to do with all this scientific notation. So first off, I want you to take 2.1 times 84.01 and divide by 6.022. So again, multiply those numbers on top that I have parentheses around, divide by 6.022. And when you do that, you get 29.29608,104. And we've already said you need 2 significant figures. So that will round to 29. That rounds to 29. Now we have to deal with our exponents. And for the exponents, I see that we've got, trying to change colors here, 10 to the 24th divided by 10 to the 23rd. Well, you know from doing our scientific notation, when you divide exponents, you subtract, so that is 24 minus 23, which is 1. 24 minus 23 is 1. Now we have to put that in proper scientific notation. So I'm going to move my decimal to give me 2.9. Since we moved the decimal left and made our number smaller by 1 spot, that must be added back to the exponent. So 2.9 times 10 to the 2 grams of baking soda. And that is our final answer. That is our final answer.